So we're going to do some examples that are like the problems in homework 7. So now you have homework 7 solution. You've already worked on it. It's been a while. So let's do some examples that are similar and make sure that you have a good feel for how to work these problems if there's any question at all. Okay, so our homework 7 started out with a standard block configuration, and we were going to design a G sub C in order to achieve a certain set point. So we wanted Y to go to Y set point. Okay. All right, so basically the idea for this was that you would first of all start with no disturbance. So we started off with a case of W equals 0. And we wanted to, with a certain GP, design the closed loop system poles to be some set value. So you could have had a case of like ITAE. For our actual homework number 2, we set them at a value, a set value. We used -2, but anything like that, we could also, if we have a system of 2 or greater, use the dominant pair, which is really just a subset of direct root assignment, something like that. Okay, so let's do an example where we have a S plus 2 on top, and we will have an S, let's say, minus 10 on bottom, something like that. Okay, all right, so developing the equations, we first want to see how many free S's are given to us by GP, and in this case it's 0. We have no free S's. How many free S's are needed? In this case 1, because we're doing a set point and we have no disturbance. Okay, so we have 1 free S needed. Okay. All right, so that means that we can write out our trial designs. GC of S is actually going to start off with a KC over S. If that doesn't work, you would have a KC over S times S plus A on the numerator. If that doesn't work, then you will have a KC S plus A S, and you'll have to add something on the denominator. Okay, so the general procedure for this, since we are using the standard configuration, we will be able to write out our QCL, and that will be P sub P, P sub C, Q sub P, Q sub C, just like that. And then we can plug in the different elements, or GP and GC. Okay. All right, so let's do that. So the P sub P element is the S plus 2. The P sub C element for our first trial design is KC. And then we have the QP, which is S minus 10, and then the QC, which is just the S. Okay, we set that equal to 0, and then we multiply, simplify it, and evaluate it with the necessary and sufficient conditions. Okay, let's do that. So we have here an S squared, and then we have a, it looks like a negative 10S plus a KC times S, and then a 2KC, all that equal to 0. Okay, so the question is, does this one work? And I'm going to condense this together. All right, so usually when we have a single parameter and we have 2 equations to satisfy, that may not usually work, but in this case, it's going to work as long as we choose a careful value of KC. Now, it also depends. If I wanted to do ITAE, I may be somewhat limited in that. I may have to advance up to a different design to have more control over this equation. But if I just wanted to satisfy this equation and the necessary sufficient conditions, I can do that. And it does depend on this right here. Okay. All right, so for example, if we wanted to just look at the necessary and sufficient conditions, then we would have KC greater than 10. So as long as KC is a value greater than 10, this will be satisfied. It'd be positive. And then for 2KC greater than 0, as long as KC is a positive value itself, this one is satisfied. So say we choose KC equal to 25. That should satisfy both, although one more note about that, if we wanted to pick with ITA choices, we couldn't really satisfy using this trial design. We'd have to move up. Okay. Okay, so let's say now we have a case of a disturbance. So again, our GP, S plus 2, S minus 10, we're going to use the same GP that we were just looking at. Again, we still want to go to a certain specified set point, but now we have the case of a disturbance that is a stepwise constant. Okay, we were talking about this before in our free S video, and we actually want to look at the derivative of the disturbance. If that is one derivative, we need to be 0 almost everywhere. We need one free S. We actually need one free S over here anyway. To accommodate that set point. Okay, so this actually doesn't change anything about our technique that we were just looking at. Our trial designs are exactly the same because again, we just need that one free S. Now what if we had a case of a disturbance that is a stepwise constant, and we'll make that 1, and we have a second stepwise constant that is a ramp term. Okay, so this is time varying, and this is also time varying as a coefficient of the ramp term. Okay, so this can change values multiple times very quickly. However, we will evaluate it the same way that we did a second order or a first order polynomial. So the second derivative of this disturbance is going to be 0 almost everywhere. And again, just need 2 free S's. Are you going to see the effect of this disturbance term with your control design? Absolutely. You can't get away from that. But knowing that this is a disturbance and we really don't know when it's going to change value or how often, you just have to do the best that you can with your controller. So given the information that you have. Okay, so saying that we have the same plant, we have the same control task, we just have this new disturbance, let's list out those trial designs. Okay, 2 free S's total needed, not 3, 2. We don't add them together, it is choosing the larger of the 2 control task needs. Okay. All right, so the first one will be KC over S squared. If that doesn't work, KC over S squared, and we'll have an S plus A term on the top. And if that doesn't work, that is our third. We have a S plus B term added on the top as well. Okay, so then we would evaluate this exactly the same way that we were talking about doing the problem that was in the style of the first problem of homework 7, you would just plug this into your QCL, whichever equation that happens to be. If we're not using the standard configuration, expect that this could be different, and you would have to figure this out, what this equation is. Okay, and then you would plug it in and evaluate your necessary and sufficient conditions. Okay, one new kind of problem that I'd asked in this homework was giving you certain poles and certain zeros and asking for you to write out what GP is. Okay, so that's really coming down to the knowledge of what a pole and what a zero is. So a pole is any kind of root of the polynomial on the denominator, and the zero is the roots of the numerator's polynomial. So let's say I needed let's say 3 poles at 0. Let's say 2 poles at -2. Let's say I have 1 0 at 0. And let's say that I have 2 zeros at, let's say, +4 and +25. Okay, so that's quite a range. All right, let's just go through here. 2 zeros at +4 and +25. Okay, so I'm going to have an s -4, and that's my 0 here for the +4, and s -25, because I want to think about solving this to get that root. So that's where the negative sign is coming from. Okay, so I've taken care of these. 1 zeros at 0, that is just an s by itself. So think of that number being a 0, then you're just left with the s by itself. And if this were on the bottom, it would be a free s. Okay, so we've taken care of that. 2 poles at -2. Okay, so I have an s +2, and then I can go ahead and square this because I need 2 of them. Okay, so we've taken care of that. And then we have 3 poles, 3 free s's at 0. Okay. All right, so talking about the pole zero cancellation, can we do this? Well, it's actually at 0. So 0 is kind of an iffy point, but as we learned in the first half of the semester, a system root at 0 is not really a stable place. Usually it leads to some kind of marginal stability. If we have initial conditions, it can be unstable. So I would not cancel these. Okay. All right, let's do another one. Okay. Oh, and we did that one. Okay, so let's say we have 1 pole at -4, 1 pole at 52, just a different number out there, 2 zeros at +2, and we'll add 1 more pole in there. 1 pole at, or actually let's do 2 poles at ±j, like a complex j. Okay. All right, so let's start here. We have 1 pole at -4. So we have an s +4. Solving that, we would get a -4 for s, and there's our pole. So we've got that. 1 pole at 52. Got that. Okay, 2 zeros. So this is on the top now at +2. So we've got s -2, and we can square that. Okay, and then we have 2 poles, and this is the complex plus or minus j. So let's think about this before we write it in here. Okay, so we've got s plus j and s minus j. So if I were to multiply this out, I would get s squared, and I would get minus j squared, and then I would get plus js minus js, and these would cancel out. And then the j squared, since it's the square root of -1, is just the -1. So that would be minus -1 s squared plus 1. So we can write that in just like that. So this is actually 2 poles, even though this is not squared. We can think of that being squared. Okay, all right. So I think we've pretty much covered everything. Again, if you were dealing with ITAE, you would look at the certain ITAE row from the table, being s squared plus, depending on if you're looking at the ramp or the step input, which always would be specified. Some value here and some value here, of course, also omega n would need to be specified. If you were dealing with the root assignment directly, you would need to expand the roots. Say I wanted one at -2 and one at -3. I would need to expand this polynomial, and then I would get my model equation to compare against and set up my equations. Okay, and that's pretty much it